Good morning, everyone. Buenos días. My name is Daniel Schild. I'm the president of the International Linear Algebra Society. It is my great pleasure and honor to introduce to you today's speaker, Professor Anne Greenbaum of the University of Washington. Anne Greenbaum received her PhD at the University of California, Berkeley, under the direction of Beresford Parlett. Then she worked at Lawrence Livermore National Lab, and at the Courant Institute before she came to the University of Washington. Among her honors, she received the Bolzano Medal from the Czechoslovak Academy of Science in 1997. And she was the Sonia Kovalevskaya lecturer a few years ago. She's a Science Fellow. Professor Greenbaum has had a tremendous impact in the field of numerical linear algebra, and especially on the study of iterative methods for the solution of non-symmetric and non-normal linear systems. Today, she's presenting the ILAS lecture at the JMM titled, Are Iterative Solvers Backward Stable? We'll find out.
Thanks, Danielle. Okay, thank you, Danielle. Yeah, I'm not sure you'll find out today if iterative linear system solvers are backward stable, but at least we will discuss the question. So some of my colleagues working on this are Diksha Adil, Ethan at ETH in Zurich, Ethan Epperly at Caltech, and Chris Musco at NYU. We have weekly Zoom meetings to discuss this issue. So I guess the first question is why would anybody care? Iterative methods are usually used when you only need a few decimal places of accuracy. On the other hand, if we could sort of tame iterative methods, have a good way of finding really good what's called preconditioners, maybe they could actually replace direct solvers. And then we would want, if you type A\B in MATLAB, you don't want to get 2 decimal places of accuracy. You want to get the full machine precision. So that's why I'm interested in this question. Now, I think I mentioned in the abstract that I often have arguments or heated discussions, let's say, with my colleagues about whether certain iterative methods are or are not backwards stable. Part of the reason for that, not the entire reason, is that the definition of backward stability, there's no one definition, and sort of the definition that people use for the most part is vague. It's not a precise definition. One can make it precise, but then you almost always run into cases where algorithms that give just what everybody would agree is a wrong answer based on this precise definition may turn out to be backward stable. So we don't want that. So I'm going to use just a vague definition, which I will give later. Okay, then I'll talk about what I call simple iteration. It goes by a lot of different names. It's sort of the simplest iterative method you can come up with. It's usually named based on what you use as the matrix splitting or preconditioner, the classical methods, Jacobi, Gauss-Seidel, SOR. And then I'll talk a little bit about updated residual methods. These are methods, well, this would include a lot of things, actually. It includes like the method of steepest descent and the conjugate gradient method. And these are methods where rather than computing the residual B minus A times your approximate solution at every step, you use an update formula for it. And because things are being done in finite precision arithmetic, the updated vector that you call RK for a residual isn't the true residual. So you have to take that into account. And finally, I'll say a little bit about the Lanczos algorithm, and then I'll summarize. And it's a small audience, so feel free to interrupt with questions at any point. Okay, so first question, who cares? As I mentioned, iterative methods are usually used when only a few digits of accuracy are needed. However, assuming exact arithmetic, methods like CG and Lanczos produce the exact solution in at most n steps, and if matrix vector multiplication requires only O of n operations, then for a large class of matrices, if this actually worked, we would have an O of n squared linear system solver, better than the optimal 2.3, whatever the number is now, okay? Unfortunately, in finite precision arithmetic, this does not necessarily hold, so this doesn't work. On the other hand, if a good preconditioner can be found, then iterative methods may obtain a very good approximate solution in O of 1 iterations. And if the matrix and preconditioner can be applied in time O of n, then we would have an O of n linear system solver for a class of matrices. Well, that if a good preconditioner can be found is a big if, but there have been some very interesting results, I think, recently with sketching for preconditioning. Mainly, it's been used for least squares problems where there are far more equations than unknowns. But with the least, whoops, I did backwards, sorry. With the least squares problem, what they do is they convert it into the preconditioned normal equations. Now, usually numerical analysts frown upon solving the normal equations, but we're not actually forming the normal equations, and if the preconditioner is good enough, it may not be such a big deal that the condition number of the normal equations is the square of that of the original matrix. And just to put in a plug for talks about sketching and related things, there's a ILS special session on randomness in numerical linear algebra here on Saturday. Okay, so backward stability. This is what we want. We have a function f that maps, I'll say, real n, I keep hitting the wrong one, real n by n matrices and real vectors to a real vector. These could be complex. I just chose real for the talk. So f takes a non-singular, an n by n non-singular matrix A and an n vector B, and produces a vector y that satisfies ay equals b, or produces the vector y that satisfies ay equals b. An algorithm for computing f of a, b, implemented on a computer with unit round-off u is said to be backward stable to level epsilon, and epsilon will, of course, be a function of u. If for all a, b in the input space, it produces a vector y hat such that y hat is the solution to a slightly perturbed problem. A plus delta A times y hat equals B plus delta B, where the norm of delta A is less than or equal to epsilon norm A, and the norm of delta B is less than or equal to epsilon norm B. Okay, now, by a machine with unit round-off U, what I'll mean is one where where real numbers are rounded to the nearest floating point number, and the elementary operations are performed so that the relative difference between, say, A plus B and the true solution, A plus B, the relative difference is less than or equal to the machine precision. What's the reasoning behind this definition? Well, A and B are rounded anyway, so at best you have on a computer with unit round off U a matrix A plus delta A on the right-hand side, B plus delta B, where the entries of delta A and delta B are less than U times the corresponding entries of A and B. Now, that may not be such perfect justification for iterative methods, because with iterative methods, although B is usually stored, the matrix A may not be. So the accuracy of an iterative method is going to depend on the accuracy of matrix vector multiplication, which might be done in the standard way, or it might be done in many non-standard ways. One often uses a matrix splitting or preconditioner, a matrix M that approximates A, but for which linear systems with coefficient matrix M are easy to solve. For example, M equal to the diagonal of A or the lower triangle of A. Okay? Triangular systems are easy. And then one might ask, well, will the attainable accuracy depend only on the accuracy of multiplication by A, or will it depend on multiplication by M inverse A? Well, there's a theorem due to Riegel and Gasses that says the minimum over epsilon, such that some A plus delta A y hat equals B plus delta B with norm delta A and norm delta B less than or equal to epsilon times norm A and norm B, is given by this expression, which I will refer to as a relative residual norm. The norm of B minus A y hat divided by norm A, norm y hat, plus norm B. So an algorithm for computing A inverse B implemented on a computer with unit round off U is backward stable to level epsilon if for all A, B in the input space, it produces a vector y hat that satisfies the relative residual is less than or equal to epsilon. Now, that's what the residual satisfies. How is that related to the error, the difference between the true solution A inverse B and y hat? Well, if the relative residual is less than or equal to epsilon, then that implies that the relative error, norm A inverse B minus y hat over norm y hat plus norm y, is less than or equal to the condition number of A times epsilon, where the condition number is the norm of A times the norm of A inverse. The other direction does not hold the other implication in the other direction. Now, one question one might ask is, as I mentioned, we often have a matrix splitting or preconditioner. We could think of our problem not as solving AX equal B, but as solving M inverse AX equals M inverse B. Well, could we then expect the relative preconditioned residual norm to be less than or equal to epsilon? That would imply that the relative error is less than the condition number of M inverse A times epsilon, and the condition number of M inverse A may be much smaller than the condition number of A. So we could get even better results, perhaps, with iterative methods. Okay, so now comes the inexactness in the definition. We'll say that an algorithm for solving AY equals B is backward stable if, when implemented on a machine with unit round off U, for every A, B in the input space, it produces a vector y hat such that the norm of the relative residual, this is not pointing anymore, okay, such that the norm of the relative residual, oh, there it is, here, is less than or equal to, I'll say, a moderate size constant or function of n times the machine precision plus O of U squared. Well, of course, a moderate size constant is not a precise definition. In some places, instead of saying a moderate size constant, they try to make this more precise by just saying it should be big O of u, okay, meaning some constant times u in the limit as u goes to 0. But I think that can lead to results that we don't always like, results where you get what almost anyone would call the wrong answer, and yet the algorithm by that definition may be backward stable. So I'm going to leave it vague. Okay, so C of n is a moderate size constant or function of the problem size n. And, well, one can do a lot of tricks with crazy norms, okay? And so I'm going to require that this is a norm that people might actually be interested in. For example, I mean, the most common examples, of course, are the 2 norm, the infinity norm, and the 1 norm. There are plenty of other norms that people might be interested in. But I don't, if you start allowing norms, say, that depend on A and even on B, you can make the norm of this thing small when the order of magnitude of y hat is nowhere near correct. Okay, so we'll leave that much vagueness in the definition. Now, a hallmark of this definition is that the residual is small even when the matrix A is ill-conditioned, okay? The error will depend on the condition number of A, but the residual should be small, even independent of the condition number of A. But that's also a little bit hokey, because, of course, one could always define the input space as consisting only of matrices with, say, condition number 10, and then it's not so exciting that the residual is small, independent of the condition number. So perhaps one should add to this definition that there's always an implicit restriction in the input space on what the condition number of A can be. A cannot be a numerically singular matrix, meaning that as soon as you round it, you might get a singular matrix, because then who knows what you'll end up with. So perhaps one should add to the definition that the only restriction on the condition number of A allowed in the definition is that the condition number of A be less than a moderate sized function of n divided by the machine precision. Yeah.
This is a different constant than the one.
Yeah, it can be a different constant, sure. Thanks. Other questions? Okay. And of course, for iterative methods, on the other hand, we certainly do want to allow restrictions, like on the condition number or other properties of the precondition matrix. If it has to hold for ill-conditioned preconditioned matrices, the iterative method may take so many steps that nobody would want to use it in the first place. So we'll certainly allow restrictions on the preconditioned matrix. Okay, so I'll start by saying something about simple iteration. This little movie, by the way, is from a book by Tim Chartier and me about numerical analysis. We're using Jacobi's method to morph Jacobi into David Young, who worked on SOR. Okay, so simple iteration. We write the matrix A as M minus n, where M is maybe the diagonal, the lower triangle of A, something that is easy to solve. Given an initial guess, why not, for the solution, we advance the approximate solution by solving a linear system. M times yk is nyk minus 1 plus b. Very simple, not much to it. In exact arithmetic, this converges to the true solution as k goes to infinity for all initial guesses, y0, if and only if the spectral radius of the iteration matrix I minus M inverse A is less than 1. In finite precision arithmetic, this is not necessarily the case, and it's actually pretty easy to see what can go wrong. Here's an example of a non-normal, a highly non-normal matrix, meaning it happens to be diagonalizable, but its eigenvectors are extremely ill-conditioned. And what would happen in exact arithmetic, if I tried to solve this, I was using SOR with a certain value of omega. In exact arithmetic, what happens is that the error grows from 1 initially. I had a 0 initial guess. This is the relative error. It grows from 1 to about 10 to the 28. But because the spectral radius of the matrix is 0.5, asymptotically, as we can't really point at it, but as we continue to iterate, the error would go down by a factor of 2 at every step, and eventually it would converge to the true solution. What happens in finite precision arithmetic is that, whoops, wrong one. Try this one again, here, is that the error grows to 10 to the 28. At this point, you're making yes, A is, I minus M inverse A is not. Yeah. By the way, this is an example from Nick Hyam's book on accuracy and stability of numerical algorithms. So what happens in finite precision arithmetic is pretty easy to see what goes wrong. You get to an error of 10 to the 28. You're making relative errors at this point of size 10 to the minus 16. So you've got errors of size 10 to the 12. And they don't go away. And so you start out behaving like exact arithmetic pretty much. But the error does not go down to 0 as it would in exact arithmetic. And it doesn't go down to the machine precision. Or the condition number of the preconditioned matrix was moderate. It goes down to about 10 to the 14, which is just wrong. Okay, so, but as I said, it's kind of easy to see what goes wrong. The problem is that these intermediate steps introduce such big errors and they don't go away. All right, so what does happen in finite precision arithmetic? Well, in finite precision arithmetic, you've got the same equation for yk hat, except that you've got a rounding error. In Hyam's book, he says, okay, the rounding error is going to be a moderate-sized polynomial in n times the machine precision times the elements of m and n and b. If we let h be I minus am inverse and do a little algebra, then you find that the residual b minus a yk hat is h to the k times the initial residual, which it would be in exact arithmetic, plus the sum of some rounding errors. And, well, if the spectral radius of h is less than 1, then this first term, which is the error with exact arithmetic, that would go to 0 as k goes to infinity. Let's assume that the norm of the first term becomes smaller than that of the round-off terms after k iterations. That's where our residual is going to end up. Okay, the residual is going to be bounded in this way. And finally, if we assume not only that the spectral radius of h is less than 1, well, that would imply that some norm of h is less than 1, but let's assume that a reasonable norm of h is less than 1. Then we end up with this bound on the residual that involves 4 over 1 minus norm h times the maximum of these round-off terms. All right, so some sufficient conditions to give backward stability for simple iteration basically says that you can't allow the approximate solution yk hat to grow as it did in that example that I gave. And there are a number of sufficient conditions you could give. Here are some. We would like the norm of m plus norm n over norm a to be bounded by a moderate size constant or function of n. this sort of says that the norm we're using is one in which rounding errors are small, not a crazy norm. The norm of h, we want that to be less than 1 and enough less than 1 so that when we pull out that 1 over 1 minus the norm of h and express our error in terms of the maximum round-off error, 1 over 1 minus norm h is a moderate size constant or function of n. Now, that will, condition 2 will keep yk hat from growing too large, but to make sure it doesn't really grow much at all, let's assume also that the norm of I minus m inverse a is less than 1. By enough so that the error, at least at steps 1 through capital K, does not exceed the initial error. Then if the initial guess is y0 equal 1, then the norm of yj hat will not grow by more than a factor of 2 times the norm of y. And with all these assumptions, one can show that a sort of relative residual satisfies what we want, and then to replace y in the denominator by yk hat, that's where we have to make the assumption that the matrix is numerically non-singular, that its condition number is less than or equal to 1 over a moderate size function of n times u. So under these conditions, simple iteration for solving ay equals b is backward stable. But if we make only these assumptions, unfortunately, the attainable error depends not on the condition number of m inverse a, but on that of a. Now, there might be special preconditioners where you could get this nice result that the error depends on the condition number of m inverse a, but in general, you do not. This is just an example I cooked up where the condition number of a is 10 to the 8. The condition number of m inverse a is 2. And it satisfies the conditions I gave for backward stability of simple iteration. The red curve shows the 2 norm of the relative residual decreasing to 10 to the minus 16. The black curve shows the 2 norm of the relative error not landing at 10 to the minus 16 or 2 times 10 to the minus 16, but at 10 to the 8 times 10 to the minus 16. Okay, well, that's it for simple iteration. Updated residual methods. Simple iteration may be slow to converge. We can do better. Updated residual algorithms like steepest descent and, more reasonably, conjugate gradients can do a lot better in many cases. These are methods where the iteration takes the form yk is yk minus 1 plus a coefficient ak minus 1 times some direction vector, which means that the residual b minus a times yk, or rk, is rk minus 1 minus ak minus 1 times a times tk minus 1. In the method of steepest descent, we assume that a is symmetric and positive definite. Pk minus 1 is the residual or the preconditioned residual. And the coefficient ak minus 1 is chosen to minimize the a norm of the error at that step. In the conjugate gradient method, we again assume that a is symmetric and positive definite. ak minus 1 is chosen to minimize the error in the direction pk minus 1, and the direction vectors form an a-orthogonal basis for the preconditioned Krylov space, which means that we're really minimizing over that Krylov space over a much larger space than just the one direction vector, pk minus 1. One could also implement simple iteration in this form. There's no particular reason to do it. Usually there you compute the residual directly, but one could do it this way. Also, Richardson iteration, that's just like simple iteration, except you do introduce, instead of setting ak minus 1 to 1, you set it to something like 1 over the average of the largest and smallest eigenvalue of A. You use some fixed parameter. So those are all methods that fit into this category. What happens in finite precision arithmetic? Well, you update yk and make an error that is small compared to the size of yk minus 1. And you update rk, okay, using the same formula, and you make an error. But the interesting thing is that the error you make here is small compared to the size of rk minus 1 and also a pk minus 1, but pk minus 1 is usually closely related to rk minus 1. So the point of this is that when you update this rk, as rk gets smaller, the error terms get correspondingly smaller. Okay? So the round-off terms for rk hat are on the order of u times the norm of rk minus 1 hat. So what you find is that the vectors rk hat actually converge well below the machine precision. But of course, these are not the true residuals. The true residual is b minus a yk hat equals b minus a yk minus 1 hat minus ak minus 1 a pk minus 1 hat, and then minus the error a times ck, where ck, you recall, was small compared to yk. It was like u times the size of yk, or yk minus 1. Okay. So let's assume without loss of generality that we take y0 equal to 0 so that r0 equals b, and I'll assume the entries of b are floating point numbers, so that's exact. Then the difference between the true and updated residual satisfies this inequality. It's less than or equal to this sum of rounding terms, rounding errors. This bound is sharp, okay? So you can't, unlike simple iteration, you can't replace this sum by the maximum round-off term. So you must assume that the number of steps, capital K, to reduce the updated vector below machine precision is moderate, and with a good precondition, or it should be. So one can give a theorem. The norm of the difference between the true and updated residual relative to the norm of A times the norm of Y is less than or equal to u plus O of u squared times some things that involve the step number K, the accuracy C of matrix vector multiplication, and again, it involves the norm of the possible growth in yj hat, this factor theta k. If capital K is the first step at which this updated vector becomes less than the round-off terms, then we can just drop that factor and say that the relative residual is bounded by this expression. So in order to get a good result here, to establish backward stability, now we must not only argue that the norm of yk hat does not grow too much larger than the norm of y, that's that theta k factor, but also that the norm of this updated vector decreases below round off in a reasonable number of steps. Well, do these things happen? Okay. So for steepest descent and CG, the norm of RK hat should decrease well below U if the inner products are computed accurately. You choose that coefficient, AK minus 1, by computing an inner product in order to minimize this updated residual in some direction. But inner products can be a little tricky. You can't guarantee in finite precision arithmetic that you get something close to the true inner product. There could be a lot of cancellation among terms. So the bottom line is, I haven't seen an example where this does not happen, but I also haven't seen a proof that it does. There's some work by Vojniakovsky on a variant of conjugate gradients in which he sort of says something like this, but he doesn't really establish that the updated vectors do become less than the machine precision. Okay, in exact arithmetic, what about the growth of yk hat? Now, in exact arithmetic, unpreconditioned steepest descent in CG, they're designed around the A norm of the error, but it turns out they also reduce the 2 norm of the error at every step, which would imply that if your initial guess is y0 and the 2 norm of the error never gets larger than the 2 norm of y minus y0, then it means that the norm of each yk is less than or equal to twice the norm of y. And one might expect something similar in finite precision arithmetic, though it hasn't been proved. Okay? And unfortunately, with the preconditioned algorithms, you're not even guaranteed this in exact arithmetic. They are guaranteed to reduce the 2 norm of L inverse transpose times y minus yk if LL transpose is the preconditioner. And so you could get some growth in the approximate solution that would enter into the ultimately attainable accuracy. Now, at least the growth in the approximate solution is limited. And so one way to sort of get around this is to use iterative refinement. If the algorithm stops making progress, you can recompute b minus a times yk hat. You'll presumably get some digits of accuracy, use it as the right-hand side to determine a value delta y, such that a times yk hat plus delta y is approximately equal to b. Okay, with that said, here is an example on the left, one that I made up, where the condition number of A is 10 to the 8th. The condition number of the preconditioned matrix, L inverse A, L transpose inverse, is 50. The red curve shows the norm of this updated vector, RK. The black curve, which lies under the red curve up until 10 to the minus 16, that's the norm of the true residual. So that looks good. It gets the full machine precision accuracy. The dashed blue curve, that's the 2 norm of the relative error, which gets down to kappa of A, the condition number of A times the machine precision. Unfortunately, in this case, not the condition number of L inverse A, L transpose inverse times the machine precision. But with a preconditioner, one can construct a problem where the approximate solution, where the error on the very first step grows by 5 orders of magnitude. On the right here is a problem where the condition number of A is 10 to the 12. The condition number of L inverse A, L transpose inverse is 8.4. You again see the updated vector RK going to 0. The true residual agreeing with that updated one, but not all the way out to machine precision, only to about 10 to the minus 10, because we lost 5 places of accuracy when our initial vector jumped from 10 to the 0 to 10 to the 5. So based on this, I guess we can't say that preconditioned conjugate gradients is backward stable, because we didn't get the full machine accuracy in the relative residual. Oh, but as I mentioned, one can apply iterative refinement to this problem when it stops making progress. And then we were able to get the full machine precision. So CG followed by iterative refinement may be backward stable.
Question.
Yes?
At each step of iterative refinement, you do another CG, correct?
Sorry?
At each step of iterative refinement, you do another CG.
Yeah, that's what I was thinking. Yeah. Yeah. Yeah, the big thing is you recompute the residual, the true residual, which if you recompute the true residual, if you carry along the true residual instead of the updated one, that actually affects the convergence of CG. It makes it go slower. So you don't want to do that at every step. But when it stops making progress at all, of course, that's a good time to do it. Yeah.
So how do you monitor?
Well, I don't know. How do you monitor? You can measure the residual. If it stops going down, you say, maybe I better try something else. Yeah. Other questions? All right. That's it. All right, I want to say just a little bit about the Lanczos algorithm. This is a picture of Lanczos. It's mathematically equivalent to conjugate gradients, but the analysis of the Lanczos algorithm in finite precision arithmetic really applies to a very different implementation than conjugate gradients. The idea is that you construct an orthonormal basis for the Krylov space. Here I'm not using a preconditioner, though I should. Hardly any analysis of preconditioned Lanczos has been done, so I'll just write it without a preconditioner. Let QK be the matrix whose columns are these orthonormal basis vectors. Then you have a relation, A times QK is QK times a symmetric tridiagonal matrix consisting of the recurrence coefficients plus a remainder term. So you approximate the solution to AY equal B at step K by QK TK inverse norm B times E1, and this is the optimal approximation in A norm from the Krylov space. The residual then, take B minus AQK times TK inverse norm B E1, and you're, excuse me, and you're left with this term. Okay, so you're left with this term. I'll assume from now on that norm B is 1 so that I don't have to write that so often. What happens in finite precision arithmetic? Well, you almost have this 3-term recurrence, but you have a small rounding error here. What does that do to things? So the norm of FK is tiny, but the columns of QK hat may lose orthogonality completely. They may even become linearly dependent. The tridiagonal matrix TK hat that's generated in finite precision arithmetic may not look anything like the exact arithmetic version. Still, QK hat, TK hat inverse E1 may be a good approximation to the solution A inverse B. Page analyzed the rounding errors, which is fairly simple to do. He showed that he gave a bound on the norm of this matrix FK. Ideally, the QJs would have norm 1. QJ hat has norm almost 1. The more interesting result, I think, is that he showed that the eigenvalues of this matrix TK hat from finite precision that looks perhaps nothing like the TK you would get in exact arithmetic lie essentially between the smallest and largest eigenvalues of A. Okay? So Druskin, Knieznerman, and I did some work comparing the 2 norm of the residual in finite precision Lanczos to that. We're not going to compare it to what would happen with exact arithmetic for that problem, but we compared it to what would happen with exact arithmetic applied to the tridiagonal matrix that is actually generated in the finite precision computation with initial vector equal to the first unit vector. And we were able to show that the residual, the norm of b minus a times yk hat, is less than or equal to something that we would have with exact arithmetic, essentially, except that now we have this kappa tilde that takes account of the fact that the eigenvalues of tk hat may not be exactly between lambda min and lambda max of a. And we also have a rounding term. So the proof sketch is this beta k plus 1 times the k1 entry of tk hat inverse is the norm of the residual at step k of exact Lanczos applied to this tridiagonal matrix with right-hand side E1. And it follows that we have this bound on that quantity, and then the rest just follows from the rounding error analysis that Page did. All right, well, that looks pretty good, but only pretty good. There are some limitations. For one thing, we're assuming that yk hat, our approximate solution, is exactly qk hat, tk hat inverse times the first unit vector, but of course there's going to be error in evaluating that. We didn't incorporate a preconditioner. If Lanczos is applied to L inverse A, L transpose inverse, and matrix vector multiplication means solve with L transpose, multiply by A, solve with L, each done in a standard way, then Page's analysis of where the eigenvalues of tk hat lie must be modified. And so if you want to use this result, we're going to have to assume that kappa of A is small enough so that even when we replace it by kappa tilde, which in fact is a function of k, but it involves k times the machine precision, or some power of k times the machine precision, this first term still goes down in a reasonable number of steps to where we're left with only the round-off term. So bottom line, I would say this does not establish backward stability of the Lanczos algorithm, and I would say that's still an open problem. Some recent results, an early result by Druskin and Knieznerman dealt with more general functions than just A inverse B, and a recent paper by Musko-Sidford expanded upon that, evaluating finite precision Lanczos for evaluating f of A times B. It doesn't seem to give stronger results for linear systems, but it's a more general result. Knieznerman in 1996, and then very recently, Chen and Trogdon, considered conditions under which finite precision Lanczos actually does generate almost the same tridiagonal matrix as exact Lanczos for the same A and B. Page, very recently, showed that after some step, say capital K, there is an approximation qk hat times zk such that the relative residual is bounded in this way. But this is not the Lanczos approximation. He does derive a relation between the two, but it still does not incorporate a preconditioner, and there's no bound on how large k must be. So again, I would say I don't consider that a proof of backward stability, not yet. All right, summary. With assumptions that prevent yk hat from growing too large and that ensure that in exact arithmetic the residual is reduced by a reasonable amount at each step, one can show that simple iteration is backward stable. Updated residual methods like steepest descent and CG need not only for yk hat not to grow too much, but for this updated residual to be guaranteed to converge below the machine precision in order to get backward stability. Analyze the accuracy of computed inner products to determine if the updated residual does indeed go to 0 or something less than the machine precision. If the preconditioner is LL transpose, then the norm of yk can grow. It can grow to the condition number of L, but if we're assuming the condition number of A is less than 1 over U, then the condition number of L is probably going to be less than 1 over the square root of U. So you can recompute the residual and use iterative refinement to improve accuracy. Lanczos is mathematically equivalent to CG. The relation in finite precision arithmetic, especially with a preconditioner, needs to be further explored. And finally, I would like to thank the International Linear Algebra Society for all of their work in promoting linear algebra and its application.